All right, substituent effects on acidity. We're going to look at some specific things here. We've seen how carboxylic acids are much more acidic than alcohols, for instance. Presence of that double bond and its resonance. And so what happens is we put other substituents. If we compare acetic acid, again, that's vinegar. Probably familiar with that if you like dill pickles. Those kinds of things, they're all preserved in vinegar. So acetic acid, pKa is 4.8. If we go to the trifluoroacetic acid derivative, pKa goes to minus 0.23. Big difference between those two numbers. Now, basically that's a difference of 5, roughly. And remember, this is in pK units, so that's a 10 to the 5th difference in acidity. It's 100,000 times more acidic is trifluoroacetic acid versus acetic acid. Remember, pKa equals minus log of the Ka, so it's base 10. Now, let's look at these substituents as we move away from the benzoic acid. So we now have a longer carbon chain. If we have the chlorine at the 2 position, what we see is a pK of about 2.86. Now, not as dramatic as the trifluoro, but still a huge difference comparing these two. Butanoic acid is similar to acetic acid. So you can say there's roughly at 2 orders of magnitude, making it 100 times more acidic. If we go to the 3 position, the acidity is reduced. The pKa goes up. Don't forget that inverse relationship to about 4. Now, not quite 4.8, almost an order of magnitude in difference. And then we get over here to the 4 position. By the time at the 4 position, there's not a terrible lot, 4.5 versus 4.8. So not a huge difference. And then there's one more group that we want to talk about, and that is the aryl derivatives. If I take a benzoic acid, I'll switch pens here. A benzoic acid, and we look at a para substituent when X equals H versus O methyl versus nitro. So what do we have here? We have benzoic acid, hydrogen, that's our standard. That has a pKa of about 4.2. If we go to the methoxy, it's an electron donating group. It's pushing electrons toward the carboxylic acid, and that would destabilize the anion, and it goes up to 4.5. So not huge, but 10, the difference here, remember, is 10 to the 0.3, so that's not just 0.3. I'll let you plug that into your calculator and see what that number is. Now, the nitro group, where does it go? It's strongly electron withdrawing. So it's removing electron density and will stabilize the carboxylate or the benzoate anion, specifically in this case, and the pKa goes down to about 3.4. So here you're at 10 to the 1.1 difference. So it's a little more than 100 times more acidic than the methoxy group. So those trends are consistent in terms of acidity with what we'd seen before for electrophilic aromatic substitution. So you should recognize those distinctions. The lone pairs on oxygen are pushing electrons. If the methoxy is here, they're pushing electrons into the ring. You should be able to draw that resonance form. And the same thing with the nitro. Remember, the nitro looks like this. So it's strongly electron withdrawing because of the formal positive charge and also by resonance. All right, so those are substituent effects on acidity. We need to be able to predict those.